Hi folks, Mrs. Gates here. Today we are going to be talking about the equations of motion. There are three basic equations that you need to know. You need to know where they came from, and you need to know what their variables mean and how to use them. Let's look at the equations. The three basic equations of motion are shown here. Let's talk about what their variables mean, and then we'll talk about where they came from. The first variable we see is v. V is going to represent the velocity of a moving object. Okay. The next variable is v with a subscript 0. This means the velocity at the time 0 or the initial velocity. A represents our acceleration. T represents time. And delta x means the change in position, x minus x0, or the displacement of our object. In order to understand where these equations came from, we'll start with our understanding of a velocity-time graph. Consider the graph shown here. The y-intercept of this graph represents the initial velocity for a moving object. And recall that on a velocity graph, the slope of the graph is always equal to the acceleration, or a, for our object. That means if we were to write an equation that represented this line in y equals mx plus b, or slope-intercept format, we would simply be saying that y represents our velocity, our slope is the acceleration, our x variable is time, and our y-intercept is the initial velocity. This gives us the first equation for our equations of motion. Velocity equals acceleration times time plus the initial velocity. Our second equation of motion also comes from our understanding of a velocity-time graph. Remember that the area underneath a velocity-time graph is always equal to the change in position or the displacement of an object. That means if I want to find the displacement, or delta x, for my object, I simply need to find the area under the graph. In this case, I will divide this area into the area of a triangle plus the area of a rectangle. I'll write it this way. The change in position is the area of this rectangle plus the area of the triangle. Okay. If we're looking at a particular time t, this point is our initial velocity, which means the area of this rectangle is actually equal to the initial velocity multiplied by the time, width times height. The area of a triangle is 1/2 base times height. So we have 1/2. The base of this triangle is the time, and the height of the triangle is, let's draw a dotted line in here, the difference between the final velocity and the initial velocity. I'm going to write that like this, v minus v0. I can simplify this a little bit. Particularly, I can remember that in my original equation, my equation number 1, we had something very similar to this. In our original equation, let me use a different color for that. The first equation we had said that v equals v0 plus at. That means that v minus v0 is equal to acceleration times time. So I'm going to replace v minus v0 with acceleration times time. That means that my equation for the change in position, or the area under my graph, is the initial velocity times time plus 1/2 of t, now multiplied by acceleration times time. And if I look at that term, I can simplify that a little bit. I have two t's and one a, so I can rewrite that in its final form like this, plus 1/2 a t squared. And this is the second equation of motion. The change in position is equal to the initial velocity times time plus 1/2 of acceleration multiplied by time squared. The third equation of motion comes from when we combine these first two equations to get an equation that does not include time. In order to do that, we'll take our first equation of motion and solve for time. That would give us time equals v minus v0 over a. We can find an equation without time by then taking this expression and plugging it into our second equation every time we have t. That gives us an equation that looks like this. Delta x equals v0 times v minus v0 over a plus 1/2 a v minus v0 over a squared. All right, this looks like a mess. Let's start cleaning this up a little bit by multiplying both sides of our equation by 2a. That will get rid of some of our fractions. So we're going to multiply everything by 2a, and 2a. Okay, I know that's a little bit messy. Let's go back to green. Once we've done that, on our left-hand side of our equation, we get 2a times the change in position. This first term, this a cancels out with the a on the bottom here, and we have 2v0 times v minus v0. Okay, our second term, the 2 and the 1/2 cancel out, and we have a squared on the bottom, and then we have 2a's that cancels with. So this actually on our second term just leaves us with v minus v0 squared. Okay, we can clean this up a little bit more by expanding these things that we have on the right-hand side of our equation. So I'm going to expand both of these parentheses, and that'll give us 2v0v minus 2v0 squared. Okay, the second term, we're going to have to distribute the square. That means we get v minus v0 times v minus v0. If you remember from algebra, that gives us something like this: v squared minus 2v v0 plus v0 squared. Okay, now we can start canceling some of these things out. So let's use another color to do that so you can tell what we're canceling. So we can combine, we have 2v0v here and minus 2v0 there. So these actually totally cancel each other out. Okay. We have negative 2v0 squared and positive v0 squared over here. And so when we rewrite this, we end up with just one negative v0 squared. And then this didn't have any other like terms, so we have plus v squared. And then over here we have 2a delta x. Okay, we're almost done. The only thing that we change about this is that usually we have this equation solved for just v squared when you see it written down. So all we have to do is add v0 squared to both sides. Okay. And I'll write our final version over here. We end up with v squared equals v0 squared plus 2a delta x. And this is our third equation of motion. The velocity squared equals the initial velocity squared plus 2 times the acceleration multiplied by the displacement. That gives us our three equations of motion. Now let's talk about how to use these equations to solve problems. We'll start with an example. A car speeds up from rest to 10 meters per second over a distance of 15 meters. What is the car's acceleration? All right. When you're looking at a question like this, a couple of things that are really important. First of all, we have to write down what things we know. Okay. The car speeds up from rest. From rest means that the velocity was 0, and that was at the beginning. So this is actually telling us that our initial velocity was equal to 0. Okay. It speeds up from rest to 10 meters per second. That's our final velocity, 10 meters per second. Over a distance of 15 meters. That's going to be our change in position. Okay. So these are the three things we know. All right. What we want to know is the acceleration. All right. The key to solving an equation, solving a problem using the equations, is then to pick the correct equation. So you look at the variables that we know, v0, v, delta x, and we want to know a, and we need to figure out which one of these three equations contains those variables. Okay. Well, as I'm looking at that, that's this last equation. This last equation is the one that has those variables in it and does not have any other variables. Okay, so let's practice plugging these things in. So v squared, v is 10. So as I rewrite this, plugging my numbers in, I have 10 squared equals v0 squared. Well, v0 is 0. 0 squared is still 0, but I'm going to write that down anyway. Plus 2. A is the thing we're looking for, and we know that the change in position was 15. Okay, all right, so let's start solving this. We're solving this for A. 10 squared is 100. 0 squared is 0. So I'm left with this term. 2 times 15 is 30. Okay. I divide both sides by 30. And we end up with A is equal to 3.3 meters per second squared. Okay, so the keys here, a couple of things. Number one, make a list of the things you know and the things you want to know so that you can pick out the correct equation. Once you have that equation, plug in the values in the correct spaces and notice what thing you're solving for. In this case, it was A. I think it's very difficult to solve an equation like this if you write the units next to each number. There's too many letters, too many things going on. So I usually write these without any units and then add the units on at the very end, making sure that I have the correct units for the variable I solved for. Hopefully that has been helpful in thinking about these equations of motion, both where they came from and how to use them. Now, go out and solve some physics problems.